All right, welcome to Math 158, Functions, Graphs, and Matrices. This is section 4.2, using matrices to solve systems of linear equations. In a previous video, we talked about solving systems either by graphing, using a substitution method, or an elimination method, linear combination method. In this video, I'm going to begin by reviewing that with the first couple of problems, and then we're going to explore how I can use matrices to solve systems of equations. Matrices may be something that you're used to, maybe it's something you're not used to. And we'll do a quick review of matrices, at least to the extent that you need to understand them, excuse me, in order to be able to solve systems of equations using them. So first of all, if I have this system, 5x plus 3y equals 25, and 3x minus 2y equals negative 4. Notice that we have a positive 3y and negative 2y because one's positive and one's negative. It's going to be easier to cancel out the y variables. So I'm going to choose to multiply the top equation by 2 and the bottom equation by 3. Now, the reason I want to do this, you'll notice in a moment, when I distribute the 2 to the 5x, the 3y, and the 25, that top equation will become 10x plus 6y equals 50. And the bottom equation, when I distribute the 3 to the 3x, the 2y, and the negative 4, becomes 9x minus 6y equals a negative 12. And then now I can add those two equations together. So 10x and 9x will become 19x. Positive 6y and a negative 6y will add up to 0, so those will cancel out because they'll add up to 0, and that will equal 38. Dividing both sides by the 19, x equals 2. Now that I have a value of 2 for the x variable, I can take that 2 and substitute that now back into any of these four equations. And it doesn't matter which one you use, okay? I'm going to just choose to substitute it into the top equation, so 5 times the x value, which is 2, plus 3y equals 25. 5 times 2 is 10, plus 3y equals 25. When I subtract the 10 from both sides, I get 3y equals 15 and y equals 5. So my solution, I can write it as x equals 2, y equals 5, and that's acceptable in my opinion, or the ordered pair 2, 5. I'm okay either way that you want to write that. Okay, solving the system using the elimination method. In number 2, now you'll notice that in number 1, I wanted to eliminate the y's because one of them was already positive, one of them was already negative. In number 2, I might decide, you know what, let's eliminate the x variable. So I'm going to multiply the top equation by 5 and the bottom equation by 4, so that when I distribute the 5, I'll get a 20x. When I distribute the 4, I'll also get a 20x. Now you're correct that one of them is going to want to be negative. I can decide that now. I don't need to decide that now. In fact, what I'm going to choose to do is I'm going to choose to wait. If I simply distribute the 5 to the top equation, it becomes 20x plus 15y equals 145. And when I distribute the 4 to the bottom equation, it will become 20x plus 28y equals 148. Now, one of those equations needs to be positive and one of them needs to be negative. Sometimes I wait until this point to decide which one I want to be positive and which one I want to be negative. I'm going to choose to make the top equation negative. In other words, I multiplied everything by the negative. That backs up and says, well, maybe if I multiplied by a negative 5, I would have been okay. So now, the 20x and negative 20x will add up to 0, so they will cancel out. Negative 15y and a positive 28y is 13y. And then negative 145 and a 148 is 3. Dividing both sides by the 13, y will equal 3/13. Yes, I did my algebra correctly. If you get a crazy number like that, you can go ahead and check your algebra, make sure you did it correctly to ensure you should be getting a number that's not an integer solution. We're used to we like to get integer solutions, but we may not always get them. Now, at this point, I do have a couple of choices. I can choose, I would not do this, but I could choose to take this value for y, the 3/13, and substitute that back into one of the original equations. But if you think about it, there was really no magical reason why I chose to eliminate the x's as opposed to the y's, other than I kind of had smaller numbers if I multiply by 4 and 5 as opposed to multiplying by 7. But what I could do, rather than taking the 3/13 and plug it back in, I can go back to my originals, and I'm going to rewrite them just so it's a little cleaner. And this time I'm going to do the same thing, except that I'm going to multiply the top equation by 7 and the bottom equation by 3, so that after distributing the 7 to the top equation and the 3 to the bottom equation, I'll get 28x plus 21y equals 29 times 7. And I'll use the calculator for that one. So I'm going to get 203. And on the bottom equation, 15x plus 21y equals 37 times 3. That should be 111. And then now again, I'm going to decide which equation I wish to have been negative and which one positive. I think I wanted this one to have been the negative, so it's as if I multiplied by a -3. Again, decide now, decide earlier, it doesn't really matter. The 28x minus 15x, 13x, 21y minus 21y is 0, 203 minus 111 is 92. So x will equal 92/13. So my solution is either x equals 92/13, comma y equals 3/13, or the ordered pair 92/13, 3/13. The reason that I actually prefer to go back and to do my algebra a second time is I don't have to work with the fractions other than just to write them down as my solutions. Okay, so they're solving 2x2 systems. We call these systems 2x2 because there's 2 equations with 2 unknowns. Now I'm going to use the same process, and I kind of want to show you number 3 here. Notice that number 3 is not a system of 2 equations with 2 unknown values. Notice that number 3 is a system with 3 equations and 3 unknown values, x, y, and z. So in order to do this, what I'm going to need to do is I'm going to have to decide one of my variables to eliminate. Should I eliminate the x, the y, or the z? In this case, I'm going to choose to eliminate the z's. And the reason I'm going to eliminate the z's is, you notice I have a negative z? If I take the second and the third equation, and let's do this in a color. Right, let's do this in blue. I take the second 2 equations, the second and the third, 4x minus 12y plus 2z equals -46, and 3x plus 4y minus z equals 23. Notice that when I pair those up, I've got a positive 2z and a negative z. So I can choose to just simply multiply the bottom equation by 2. The top equation won't change. The bottom equation becomes 6x plus 8y minus 2z equals 46. Now notice when I add these two together, the 4x and the 6x is 10x. The negative 12y and the 8y is a negative 4y. 2z minus 2z add up to 0, so those cancel out. And negative 46 plus 46 is 0. So I have an equation here, 10x minus 4y equals 0. And I'm going to set that aside. I'm going to take another set of 2 equations, and I'm going to choose this time to take the first and the third. The first equation is negative 2x plus 6y plus 4z equals 38. And the bottom equation is 3x plus 4y minus z equals 23. Now notice I'm set up to cancel the z's. And there's really not a decision here. Since I canceled the z's over here in that blue work and came up with an equation in terms of only x and y, I need to also eliminate the z in this green work that I'm doing. So the top equation will stay negative 2x plus 6y plus 4z equals 38. The bottom equation will become 12x plus 16y minus 4z equals 23 times 4, 92. Now when I add these two equations together, the negative 2x and the 12x will add to give me a 10x. 6y and 16y is 22y. 4z and negative 4z add up to 0. 38, whoops, what happened there? 38 and 92 is 130. Okay. So now notice that I have the two equations, 10x minus 4y equals 0, and the equation 10x plus 22y equals 130. I'm going to multiply the top equation by negative 1, or I'm going to subtract the two equations. Negative 10x and 10x, those will add up to 0. 4y and 22y is 26y. Negative 0, or 0, and 130 is 130. When I divide both sides by 26, I'll get 130 divided by 26, which is 5. So I have a y value of 5. Now I have a bunch of back substituting to do. I have my y value. I now need to find my x value, and then I'll also need to find my z value. I'm going to take this equation here, 10x minus 4y equals 0, and I'm going to put the 5 in for the y. 10x minus 20 equals 0, so 10x equals 20, or x equals 2. So now I have an x value of 2 and a y value of 5, but again, I'm not done. Because remember, there are, back to the original up here, number 3, there are 1, 2, 3 equations, 1, 2, 3 unknown values. I also need to calculate the value of z. So now I pick one of these 3 original equations to substitute z in. And I'm just going to pick the third one since it only has a 1z. So that third equation is 3x, and remember x is 2, plus 4y, and y is 5, minus z equals 23. 3 times 2 is 6, 4 times 5 is 20, minus z equals 23. So 26 minus z equals 23. And if I subtract 26 from both sides, I'm going to run off my page here, but that's okay. I'm going to get negative z equals negative 3, so z equals 3. So my solution is x equals 2, y equals 5, z equals 3. Or I can write my ordered triple of 2, 5, 3. So notice the first piece I did in the green and the blue was to break the 3 by 3 system down into 2 equations by eliminating the z variable from 2 different pairs of equations. Then I solved the 2 by 2 system. Number 4, I'm just going to talk about number 4 since I used a lot of my space and my time here already. I just want you to think about this. I'm going to need to pick a variable to eliminate first. And I think in this case, I would probably eliminate the w's. I would probably take the first and the third equation together and simply add them. Right? So then what that's going to do is that's going to eliminate the w's. I would take the second and third equation, Same thing, eliminate the W's. I would take the third and fourth equation, eliminate the W's. After doing all that work, that brings me down to a 3 by 3 system, just like I had in number 3. And then now I have all this work that I have here in the blue, the green, the purple, and the black, and to do that all over again. What I want to spend my time in this video doing is not doing that algebraically, but to say, there's got to be a better way. Let's see if we can find a better way. So the better way that we're going to explore now is called using matrices. Okay, we're going to use matrices here. So let's take a moment and talk about what a matrix is. Basically, a matrix is an array of numbers with m rows and n columns. Okay, that's helpful. And also the plural of matrix is matrices, kind of like the plural of index is indices. The plural of matrix is matrices. So let's suppose that I have a matrix that's 2, 4, 6, 3, -5, 9. Notice that this matrix is an array of numbers. There are rows, there are columns. In fact, there are 2 rows and there are 3 columns. The rows are 2, 4, 6 and 3, -5, 9. 2, 4, 6 is the first row, 3, -5, 9 is the second row. Notice that there are 1, 2, 3 columns. 2, 3 is the first column, 4, -5 is the second column, and 6, 9 is the third column. So because this matrix has 2 rows and 3 columns, we would say that this matrix is a 2 by 3 matrix. Those would be the dimensions of the matrix. And there's a lot of matrix algebra that we can do, and I'll show you a little bit here in a moment, but we're not, the purpose of this video is not to do a lot of matrix algebra, but to become familiar with matrices enough to use them to solve systems. Now, one of the values of matrices is it allows me to use a large quantity of data more efficiently. All right, what's a row matrix? Basically, a row matrix is a matrix with 1 row. So I have this matrix, it's got 1 row, 1, 3, 5. Notice it's a 1 by 3 matrix because there's 1 row, 3 columns. Because there's only 1 row, it's called a row matrix. If I've got a matrix like 2, 6, 9, that's a 3 by 1 matrix. Notice it only has 1 column, therefore that's called a column matrix. What a square matrix is a square matrix is a matrix where the number of rows and the number of columns are the same. So there's 2 rows, 2 columns, 3 rows, 3 columns, 4 rows, 4 columns. You'll see the pattern very quickly. So 2, 6, 9, 3 is a 2 by 2 matrix. That is a square matrix. The entries are all of the numbers. 9 is an entry, 3 is an entry. In fact, 3 is the entry in the second row, first column. Now, for matrix addition and subtraction, I'll talk about them here since they show up here. Suppose I have the matrix 2, I'm starting with 2 all the time, I don't know why. 2, 3, 5, 6, 9, 7. And I'm going to add the matrix 1, -3, 2, -4, 6, 5. If I'm going to add those 2 matrices, first of all, in order to add or subtract matrices, your dimensions must be identical. So I've got a 2 by 3 matrix and a 2 by 3 matrix. I can add them together and I will get a 2 by 3 matrix. To add the matrices, you simply add each of the entries in the relative position. 2 plus 1 is 3. 3 plus a -3 is 0. 5 plus 2 is 7. 6 plus -4 is 2. 9 plus 6 is 15. 7 plus 5 is 12. And that's all there is to matrix addition. Matrix subtraction, I'm going to use the same 2 matrices. Is what you would think it is. I'm simply going to subtract the 2 matrices. So, you ready? The dimensions must be identical. So a 2 by 3 matrix minus a 2 by 3 matrix will result in a 2 by 3 matrix. 2 minus 1 is 1. 3 minus negative 3 is 6. 5 minus 2 is 3. 6 minus negative 4 is 10. 9 minus 6 is 3. And then 7 minus 5 is 2. And the matrices are subtracted. Okay. Matrix multiplication, just hold off on that. We'll deal with that when we need to in a future video. I don't want to take the time because this video has the potential to get long already with the things that are coming up, and I don't want to take unnecessary time doing that. We'll come back to that in a future video. Scalar multiplication, like you've heard of scaling things, right? So if I take the matrix, and we'll just stick with the matrix 2, 3, 5, 6, 9, 7, that's a matrix. The number 3 is a scalar. And so if I multiply the matrix 2, 3, 5, 6, 9, 7 by 3, simply what's going to happen is everything's going to get multiplied by 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 15 is 15. 3 times 6 is 18. 3 times 9 is 27. And 3 times 7 is 21. And there's scalar multiplication. Okay. Now, what we're going to do is we're going to use matrices a little bit differently than I showed you here. Maybe it's going to seem a bit bizarre at first, but we're going to use matrices to solve a system of linear equations. And basically what this is going to be is doing all the work that we're doing that I did back in that problem number 3 with the blue section and the green section and the purple section. And we're going to combine all of that into, believe it or not, a little bit less writing, but typically less writing means more thinking, which can be a little a little intimidating or daunting as well. There are 3 basic components, 3 basic parts to solving a system. First, we're going to represent the system using an augmented matrix. So clearly, we're going to have to spend a few minutes here talking about what is an augmented matrix. Second, and this is the biggie, we're going to perform the necessary row operations to rewrite the augmented matrix in reduced row echelon form. So yes, I hear the questions. What are the row operations that we can do? And what is reduced row echelon form? Stay tuned. 3, the simplest part, is to find and state the solutions of the system. Okay, so let's look. Whoops, wrong direction here. Let's look at a problem. Number 1. Same system we did before. Represent the system using an augmented matrix. The word augment means to change, to vary, to adjust, right? So there is another method of using matrices to solve systems that is used much less today than it used to be used. I'm sorry, I'm having trouble controlling this right now. Okay, there's a method of solving systems using equations that we don't use as much as we used to, but in that method, what you would do is you would take the matrix, you would take the coefficients, 5, 3, 3, negative 2, and put them into a matrix called the coefficient matrix. You would also take the solutions, 25 and negative 4, and you would put them into a column matrix and call that the solution matrix. Using the method that I'm going to teach you here, it's called Gauss-Jordan elimination, which you don't need to know. The method that we're going to use, first step is to create an augmented matrix, which is going to, take and blend those two together. So we're going to have 5, 3, 3, negative 2. Notice those are the coefficients. Then we're simply going to put a vertical line to separate the coefficients from the solutions and put them into one matrix. So this is the augmented matrix. Number 2, we're going to perform the necessary row operations to rewrite the augmented matrix in reduced row echelon form. Well, what are the row operations? I can interchange rows. I can multiply a row by a non-zero number. I can add a multiple of a row to another row. Those are the row operations. I will show you in a moment what I mean by that. Reduce row echelon form. What does it mean to write that matrix into reduced row echelon form? What that means, and all this options 1 4, the leading entry in each row is a 1, blah, blah, blah. Basically, what it means is we're going to start with the matrix, and forgive me to do a little back and forth here. We're going to start with the matrix 5, 3, 25, 3, -2, -4. So that's the matrix we're going to start with. This guy got a little out of control. That's the original augmented matrix. We want to get that into reduced row echelon form. And what I mean by the reduced row echelon form is that the entries here in the coefficient part will be 1, 0, 0, 1. Reduced row echelon form means all the numbers along the diagonal from upper left to lower right are 1s, and everything else is a 0. Okay? And there is a particular order that we get those in. We need to get these in order a column at a time. So in the first column, we're going to get the 1 and then the zeros. We move on to the next column, we get the 1 and then the zeros. You don't work across, you don't work down, you work one column at a time. 1 and then the zeros, 1 and then the zeros. Okay, so let's do the necessary row operations to solve this. 5, 3, 25, 3, -2, -4 is this matrix. The first thing we need to do is this element right here in the first row, first column needs to become a 1. The way that we're going to get 1s is by multiplying. The way that we're going to get zeros is to add. So where we have a 5, we need that to become a 1. So I'm simply going to multiply row 1, the first row, times 1/5. So my top row will become 1/5 times 5 is 1, 1/5 times 3 is 3/5, and 1/5 times 25 is 5. And the bottom row did not change. Should leave myself room there. Okay. Now, the next thing we need to do is we need this 0, this term here, to become 0. So this term where the 3 is going to need to become a 0. What do I have to add to 3 to get 0? Well, that's got to be a -3. So what I'm going to do is I'm going to multiply row 1. See, there's the 1 right here, times -3. Now what's going to happen is -3 times 1. Whoops. Let me go back to my black here. The top row won't change. So -3 times 1 is -3, plus this 3 is 0. -3 times 3/5 is a -9/5, plus a -2, which is -10/5. That's going to give me a -19/5. Fractions happen. -3 times 5 is -15, and a -4 is a -19. So notice we've got the 1, we've got the zeros. First column is set. Now we need to move on to the second column. And in the second column, remember what we're going to do first is the 1. So this element, that entry needs to become a 1. And what is it? It is a negative 19/5. What is it that you need to multiply by negative 19? What do you have to multiply negative 19/5 by to get 1? You would need to multiply by negative 5/19. And row 2 is the row that's going to get multiplied. Notice that once again, my top row is not going to change. My bottom row, negative 5/19 times 0 is 0. Negative 5/19 times negative 19/5 is 1. And negative 5/19 times negative 19 is a positive 5. I'm out of room, so I'm going to rewrite this over here. 1 3/5, 5, 0, 1, 5. Notice we've got the 1, we've got the 0, we've got the 1. All that's left now is to get this entry to be a 0. Notice we've got negative, we have 3/5 there. What is it that I need to add to 3/5 in order to get 0? I would have to add negative 3/5. So I'm going to multiply row 2. See, that's the row with the 1 in it. I'm going to multiply row 2 by negative 3/5 and add that to row 1. Negative 3/5 times 0 is 0, plus 1 is 1. Actually, let me just rewrite my second row here since it's not going to change. It is not going to change. Negative 3/5 times 1 is negative 3/5, plus 3/5 is 0. Negative 3/5 times 5 is a negative 3, plus 5 is 2. So now notice we have our matrix in reduced row echelon form. I call it RREF, reduced row echelon form. Okay, now I ran out of space and it runs on to the next page, but the next thing that we do is we find and we state the solutions. Well, if you remember, okay, this top row here, 5, 3, 25, that was 5x plus 3y equals 25. That's what the top row represents. This bottom row represents the equation 3x minus 2y equals negative 4 because that was my original system. Well, now down here at the bottom, the top equation is x plus 1x plus 0y equals 2, and the bottom equation is 0x plus 1y equals 5. In other words, x equals 2 and y equals 5. I don't have to do all of this. I can just see x is 2, y is 5. See, x is 2, y is 5. And there's my solution. And that's what we got the previous time. That's a lot. It's one example. That's a lot. You can see that these take some time. Let's look at a next problem. Okay. Let's solve this system. Remember, the first thing we're going to do is we're going to write this as an augmented matrix. 2, 1, 3, 1, 4, 2, 4, 4, and then 1, 2, 1, 4. Okay. So the first thing I need is I need the element where this 2 is here. I need that element in the top row, top left, to be a 1. And there's two ways in this case that I can get a 1 there. I can either multiply the entire top row by 1/2, or I could switch the top and the bottom row and just flip them. And I would rather flip them in this case, because if I multiply that entire top row by 1/2, if I divide that entire top row by 2, I'm going to get fractions. And not that I mind fractions, not that I hate them or I can't do them. I just want to avoid them as much as I can. So my first operation here is going to be to switch row 1 and row 3. So my new top row is 1, 2, 1, 4. I'm going to leave 4, 2, 4, 4 right there is the middle row. And then 2, 1, 3, 1 becomes my bottom row. And notice I have the 1. Now what I need is where this 4 is and where this 2 is, those need to become zeros. So the first thing I'm going to do is I'm going to leave my top row is 1, 2, 1, 4. This 4 needs to become a 0. I get 4 to become a 0 by adding negative 4 to it. So I'm going to multiply row 1. It's the row with the 1 in it. Negative 4 times row 1 plus row 2. Negative 4 times 1 is negative 4 plus 4 is 0. Negative 4 times 2 is negative 8 plus 2 is negative 6. Negative 4 times 1 is negative 4 plus 4 is 0. Negative 4 times 4 is negative 16 plus 4 is negative 12. Notice now I have the 1 in the first column. I also have the 0 in the first column. To get the 0 here, I'm going to need to add a negative 2 to this 2. So I'm going to do negative 2 times row 1 plus row 2. So negative 2 times 1 is negative 2 plus 2 is 0. See, we got that 0. Negative 2 times 2 is negative 4 plus 1 is negative 3. Negative 2 times 1 is negative 2 plus 3 is 1. Negative 2 times 4 is negative 8 plus 1 is negative 7. Okay. Notice that I have made a mess of my page here. Notice that I have notice that I have my first column, the 1, the 0, and the zeros. So now I'm going to move on. Whoops, I want to make that longer. Now I want to move on to the next column. So now I'm going to be looking at the second column. The first thing I'm going to do is I'm going to get the 1. Don't get the zeros first. Don't work top down. You get the 1 first. The element that needs to become a 1 is this negative 6 here. To get 1s, you multiply. To get zeros, you add. To get 1s, you multiply. To get zeros, you add. I'm going to multiply row 2 by negative 1/6. And the reason I'm going to do that is if I multiply negative 1/6 times negative 6, I'll get the 1. Now the first thing, I say that a lot, don't I? I'm going to do is I'm going to leave my first and my second row unchanged, and so I'm going to write those down. Now negative 1/6 times 0 is 0. Negative 1/6 times negative 6 is 1. Negative 1/6 times negative 12, negative 1/6 times 0 is 0, and negative 1/6 times negative 12 is 2. So notice we have the 1, we got the 0, we got the 0. The whole first column is set. Now we have this 1. Somebody's tempted to say, hey, look, we got this 0 over here. Maybe, maybe not. Okay, don't get too excited. It might stay. Okay, but it's not guaranteed to stay. Before I go on, I'm going to rewrite this matrix over here. Sometimes I try to work with it from one side of the page to the other, and I get confused. Okay. So we got the 1, 0, 0, we got the 1. Now where this 2 is needs to become a 0. I'm going to speed this up a little bit, see if you're catching on. I'm going to multiply the middle row by -2 and add that to the top row. So my middle row will remain unchanged. -2 times 1, nope, wrong, because -2 times row 2. So -2 times 0 is 0, plus 1 is 1. -2 times 1 is -2, plus 2 is 0. -2 times 0 is 0, plus 1 is 1. -2 times 2 is -4, plus 4 is 0. Okay? And then this -3 is going to need to be 0. So now the row with the 1 in it is still row 2. So 3 times row 2 plus row 3. 3 times 0 is 0, plus the 0 is 0. 3 times 1 is 3, plus -3 is 0. -3 times 0 is 0, plus 1 is 1. 3 times 2 is 6, and a -7 is -1. Now we got fortunate here. Had the 1, whoops. We had the 1, the 0, the 0. We had gotten this 1, and we were trying to get the 0 in the top row of the second column and the 0 in the bottom row of the second column. Notice we got a little lucky. The next step would be to get the 1 in the third column. Fortunately, we already have that. Get the 0 in the third column. Again, fortunately, we already have that. So we're down to our last step in this case because we did get a little lucky. We need to get that term there, that 1, to be a 0. Bottom row is not going to change, and the middle row doesn't need to change. What we do need is we need this 1 to be a 0, so we're going to add -1 to it. We're going to add the opposite of row 3 to row 1. So the opposite of 0 is 0, plus 1 is 1. The opposite of 0 is 0, plus 0 is 0. The opposite of 1 is -1, plus 1 is 0. The opposite of -1 is 1, plus 0 is 1. So remember, the first thing that we need to do is to write the system as an augmented matrix, and there it is. The second thing we need to do is to use our row operations to reduce this to reducer echelon form. The third piece we need to do is to find and state our solutions. Remember, x is 1, y is 2, z is -1. X is 1, y is 2, z is -1. That's acceptable, or the order triple is also acceptable. Either way, that's a lot of work. I have another example here with a 3x3, and I'm just going to pause, and I'll come back to it if we need to, but it gets fairly messy. Just trust me, it gets fairly messy. So it makes me think I want to find a better way. I want to find a better way, okay? The better way that we're going to use, not only do I have this 3x3 example that I could do, let's go down here. I also have number 3, a 4x4 example, which we can try. If you'd like, pause the video, try those, see if you can find your way through it. What I want to do instead, since we're doing this by video, is I want to move ahead and look at this using the graphing calculator. You'll recognize that these systems are other similar ones to what we've done. Okay, number 3 is the one we didn't just do. Number 4 is the other one we didn't just do. But so number 1 here, right? If I use the TI-84, I still need to write this system as an augmented matrix. 5, 3, 25, 3, -2, -4. Okay. Now what I can do is I can go to the calculator. Now notice my calculator over here. Let's clear this. There's a matrix button. Okay, I just press that X and the -1 button. Notice that right above it in blue it says matrix. Okay, so we're going to go to second matrix. Your calculator will hold some matrices. I want to enter this 2 by 3. So this is a 2 by 3 augmented matrix. I want to enter that into the calculator. So I'm going to go over to Edit, select Matrix A. You might have nothing there. That's okay. I'm going to select Matrix A. And the dimensions of the matrix I want to add are 2 by 3. My elements are 5, 3, 25, 3, -2, and -4. Notice I now have that 2 by 3 matrix entered. Safest thing I have found at this point, before I go on to what I'm going to show you next, do a second quit, just go back to your home screen. Then go back into the matrix menu. Now we're going to go over to math. And there's a whole lot of mathematical things that the calculator will do with matrices. You can use the calculator to multiply matrices. You can use the calculator to add and subtract matrices. Okay. What we're going to do is we're going to, whoops, hit the wrong button. Matrix, math. We're going to go down this list to the bottom of the list, and notice that C, D, E, F, those things, C, D, E, F, will do the row operations that we were just doing. Don't use those, please, not in this course. Look at option B, RREF. Do you remember what RREF stands for? RREF stands for reduced row echelon form. So if I select option B, reduced row echelon form, on matrix A, enter. Reduced row echelon form, whoops, reduced row echelon form is 1, 0, 2, 0, 1, 5. X was 2, Y is 5. That's a lot easier. I don't know that I would use that for number 1. I'd probably use my algebraic methods. But what about for number 2? Second matrix, edit. The augmented matrix again is 4, 3, 29, 5, 7, 37. Notice it is also a 2 by 3 matrix. I just keep using matrix A. But now my entries are 4, 3, 5, 7. Whoops, what did I do? 4, 3, 29. Forgot the 29. 5, 7, 37. Second quit. Math. Matrix, I meant. Math. Option B. Reduce row echelon form on matrix A. Enter. Uh-oh. I don't want fractions. I'm sorry, I don't want decimals. I really don't want decimals. Remember, with the calculator, you can press math and look at number 1, says change to a fraction. Enter, enter, and the calculator will change your solutions from decimals to fractions. Do you remember those solutions for the system at the beginning of this video? X is 92/13 and Y is 3/13. Very nice. Very nice. Let's go back and check the one that we had just done. This 3 by 3, where did it go? Did we do this one correctly? Well, let's check it out. Second matrix, edit. Now this matrix, see this augmented matrix is a 3 by 4 matrix. And I'm going to put in the values that we see here, okay? 2, 1, 3, 1. The next row is 4, 2, 4, 4. And the last row is 1, 2, 1, 4. Second quit, second matrix, math. Remember it was option B? You can just go alpha B and it will select that option. Matrix A. Did we do it right? Yes. X is 1, Y is 2, Z is -1. Okay. So I have one last example here. My pages are all kind of jumbled, I guess, right? What about number 4? Okay, number 4, notice, would be a 4 by 5 matrix. The augmented matrix, -2, 6, 4, 1, 10, 4, -12, 2, 2, -14, 3, 4, -1, -1, 8, -5, 2, -3, 3, and 14. I don't know if you're like me. I hope you're not. I start to get a little lazy thinking, oh, I got to write all these numbers. Well, can you imagine doing the whole thing out? Okay, yuck. Using the calculator, I write the augmented matrix. Second matrix, then I go to my calculator. Edit. I'm going to use matrix A again. This time, just remember, it's a 4 by 5 matrix. -2, 6, 4, 1, 10, 4, -12, 2, 2, -14, 3, 4, -1, -1, 8, -5, 2, -3, 3, and 14. So there we go. Second quit. Now, I also want to show you something else about the calculator. And I meant to do a problem before and I didn't do it, but I hope you guys understand that if you simply press enter on the calculator will simply repeat the previous command. The previous command here was RREF matrix A. If I press enter, the calculator is going to simply redo that last command. But notice, remember, keep track of the fact that we changed matrix A. So if I press enter, the calculator will now do reduced or echelon form on the new matrix A. And this will become 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, augmented with 1, 2, -1, and 4. So X is 2. Nope. X is 1. Y is 2. Z is -1. And W is 4. Okay. Using matrices to solve systems of equations, when you get to a 3 by 3 and a 4 by 4 system, that method of augmented matrices I showed you can actually be a lot more effective and efficient, but it also takes a lot of getting used to. We have technology today. The calculator will do that work for you. In my class, 158, I will expect on a test that you can do these both with as well as without the calculator. I'll expect that when you do them with the calculator, you might get messy answers like we got up here in this problem number 2. I will expect that you can change them back to a fraction and that you won't give me decimals. Okay. I also expect, or you can expect from me, that if I give you a test, it's probably going to be a 2 by 2, at most a 3 by 3, and I'm going to try to make sure it's not something that you get boiled up in the fractions and decimals and all that kind of stuff, because that's when we just revert to the technology anyway. So again, there you go. Solving systems of higher level equations, not just 2 by 2 systems, but 3 by 3 systems, 4 by 4 systems, using augmented matrices both without the calculator as well as with the calculator.